Hi, and welcome to this video about molecules. Before we get to molecules, we need to start with atoms. Atoms are the smallest unit of an element that still maintain the chemical properties of the element. This means that while atoms are made of smaller pieces, protons, neutrons, and electrons, it is the specific combination of those pieces that defines the element. Atoms interact with other atoms to give, take, or share electrons in order to fill their valence shell. When atoms share electrons, they form covalent bonds. The resulting collection of bonded atoms is what we call a molecule. Just like an atom is the smallest unit of an element, a molecule is the smallest unit of a covalent compound. We'll discuss ionic compounds later and consider why these are separate from molecules. Because most covalent bonds are formed between nonmetal elements, molecules are typically made of nonmetals, shown here on the periodic table in yellow. Noble gases are an exception here because they already have a filled valence shell and don't form bonds under standard conditions. Nonmetal elements, with the exception of the noble gases, naturally exist as molecules rather than atoms. For instance, you would rarely encounter an isolated hydrogen atom. Instead, we find hydrogen as a two-atom or diatomic molecule, H2. Each hydrogen donates its electron to form the covalent bond in H2, thus filling the valence shell of each atom. This lowers the energy of the system and is more stable than two isolated hydrogen atoms. Here, we have highlighted the elements that exist as molecules. As we so rarely encounter these elements as single atoms under normal conditions, it's common to refer to a molecular form by the element name. This means that we must use the term atomic when we want to talk about the individual atoms of these elements. For example, if we said that chlorine gas was emitted from the reaction vessel, we would be saying that molecules of Cl2 were being released, not chlorine atoms. The types of molecules that we've been talking about here are known as homonuclear molecules, molecules made up of atoms of only one element. Of course, atoms of different elements can combine to form heteronuclear molecules, which allows for an infinite number of combinations and creates chemical diversity in our world. Molecules range from small diatomics like carbon monoxide to large complex structures like proteins and DNA, which can contain hundreds of thousands to billions of atoms. While molecules come in all shapes and sizes, the important thing to remember is that the molecule is the smallest discrete unit of the compound. Let's look at a cup of water as an example. If we could shrink down to the atomic level, we'd see H2O molecules dynamically interacting with each other. Even though the molecules are attracted to each other through intermolecular interactions, the bonds between the atoms within a molecule are many times stronger since they share electrons. So we can still identify individual molecules. Here, we've circled the individual molecules in green. The same is true when we consider larger molecules like oleic acid, one of the primary fatty acids in olive oil. Again, if we could shrink down, we'd see an array of molecules interacting with each other but maintaining their individual units. This is an excellent place to stop and think about why we don't consider ionic compounds molecules. Ionic compounds are typically between a metal and nonmetal atom, where the metal gives an electron to the nonmetal. Once the electron is given away, it is no longer connected to the atom it came from. Each atom has a full valence shell. As an example, we have sodium donating an electron to chlorine to form an ion pair between a positive ion, called a cation, and a negative ion, called an anion. When in solid form, the ions are held together by a strong electrostatic interaction between a positive and a negative charge, called an ionic bond. While it is easy to imagine this happening with just two atoms as a solid, the pairs of ions are arranged in a repeating and continuous crystalline structure. In this form, each sodium ion is surrounded by chlorine ions and is attracted to each equally, and there is no longer any clear distinction of individual pairs. This is one of the reasons we do not consider ionic compounds molecules. Another way that ionic compounds are distinguished from covalent compounds is by comparing the electronegativities of the elements bonding. Electronegativity is a measure of an element's attraction to electrons. In general, this property increases as you go right on the periodic table and decreases as you go down. Ionic bonds are classified as those with a difference of electronegativities greater than 2. Before we move on, let's take a second to discuss a different ionic compound, one with a polyatomic cation, sodium acetate. Let's specifically consider if sodium acetate were dissolved in water and acetate were floating in solution. Would that be considered a molecule? While your first instinct might be yes, after all, it is a group of covalently bonded atoms, this technically is not considered to be a molecule because it carries a charge and therefore wouldn't be found in bulk on its own, like water or oleic acid. So, by the strict definition, molecules are always neutral. That being said, chemists and biochemists often use a more relaxed definition and may refer to a charged group of covalently bonded atoms, like acetate, as a molecule. Now that we have a grasp on what molecules are, let's consider when they form. New molecules form as a result of a chemical reaction. The covalent bonds of the molecules break, and the atoms reorganize and connect to form new combinations of atoms and thus new molecules. As an example, nitrogen, N2 in red, and hydrogen, H2 in blue, recombine to form molecules of ammonia, NH3. This is a chemical change. Though made of the same atoms, ammonia molecules have entirely different properties from both hydrogen and nitrogen. This is in contrast to when covalent compounds undergo physical changes, like a phase change from liquid to gas. In that case, the molecular unit stays intact, but the intermolecular interactions change, here shown with water converting from liquid to gas. Every molecule is still a unit of H2O, but they are now interacting much less in the gas phase. Let's wrap up with a review of what we've covered today. Molecules are collections of covalently bonded atoms. They are the smallest unit in a covalent compound and determine the properties of the bulk substance. Ionic compounds do not have distinct molecular units and they are not considered molecules. Charged covalently bonded polyatomic substances are also not considered molecules by strict definition. However, many chemists relax the definition when it comes to these compounds. Molecules are formed during a chemical reaction when bonds are broken and reformed between atoms. This is in contrast to when a covalent compound undergoes a physical change, in which the molecular unit stays the same, but the interactions between molecules change. Finally, let's finish with a quick test of our knowledge. Which of these substances is a molecule? Helium or oxygen? The answer is oxygen. Helium is not a molecule because it is a noble gas and exists as an isolated atom. Oxygen is a molecule because it is one of the non-metal elements that is found naturally as a diatomic, O2. Thanks for watching and happy studying!